material, I have supplement after it because that means it's not in the book. It's just what you have in front of you for your lecture notes. So your homework for this will be finishing up the problems that you have at the end of this section. Okay, did anybody not get these lecture notes? Anybody else? It's 27 towards the back. It's class 27. It's at the back of 26. It's attached to 26. Okay. So remember that I want to approve your student ID polynomial, which is number 1 in the next project, so that you don't do your whole project with the wrong polynomial. So if I haven't already checked that off, please have it done by Wednesday so I can put a little check beside it. Your next quiz is on Friday. It will start with class 23, which was quadratic functions. That was the class before our last test, and it will go through today's material. And before you come to class on Wednesday, please do exercise 110 on page 364 in our book. Okay, that's going to, I need you to review that before we do Wednesday's class. I will send out progress reports today by 2 o'clock. So basically whatever grade I gave you on your, as a summary on your last test, that will be what I'm reporting to the registrar. Okay. Any questions before we start today's material? Okay. All right, so let's take a look. Today we're doing polynomial regression. In the past, we've talked about linear regression. And this is hopefully, well, if you were here the other day, this is a graph that we worked on the other day with US energy consumption between 1960 and 2000. And I asked many of you to draw some type of curve that you thought might fit this data the best that it could be. And you all drew different graphs for that. So let's suppose we put this in, and I asked you, what's the smallest degree for the polynomial function graphed right there? What's the smallest degree for the polynomial that would be represented by this graph? What would you say? And how would you determine it? So the smallest degree. Okay. You think this could be 1? Okay. A degree of 1 means, if we go to what we learned about turning points, if n equals 1, what kind of function is it? Yeah, it's odd. What about the name for a function with degree 1? Linear, right? So do you think that this would be a good model for a linear function? And also, let's use our turning points idea. The most number of turning points any polynomial can have is n minus 1. So if we put 1 in, it says it has no turning points. Is that true for any straight line? It has no turning points? Okay. How many turning points does this have? 2. So it has a turning point right here. It has a turning point right there. So what's the smallest degree if the number of turning points is equal to 2? Right. Because the number of turning points is n minus 1. So if you have 2 turning points, n must be equal to 3. So the smallest degree polynomial that could possibly fit this data would be a cubic, x cubed, some number times x cubed. And if you go back to our lecture from Friday, we have that polynomial curve already done. I don't have my lecture from Friday, or do I? I don't have the whole thing. I think it was like 49x cubed or something like that. It might have been, let me see. I think it might have been, oh, it was Wednesday's class 25, when we did this problem. And I think the best fit, yeah, it was negative. So the function that's graphed here is negative 49x cubed plus 806x squared plus 3776x plus 2503. So notice this is the smallest degree, okay? Now, again, notice if your right arm is up, your left arm is down, you know it has to be odd. And given that your right arm is up, would that be the right model for that? If the right arm is up. That's starting to make me think now, because when that's negative, the right arm's supposed to be down. So I don't know if this really is the polynomial regression, the best model for it. That's what we worked with in Wednesday's class. So I might have to throw this back into my calculator while you're all working and see if I made a mistake here. Okay, but if I asked you what would be the smallest degree, you count the number of turning points, and that's how you get your answer. Okay, so let's take a look at this data. You'll need your graphing calculators for today's class. And then later on, I will get you a calculator if you need it. So let's take a look. Again, all the steps are outlined in this handout. So someone want to read us this data? Ed, you want to read it for us? Okay, so we have from 1975 to 2000, and as you notice, that as time went on, we definitely are seeing an increase in the number of women in the civilian workforce. If we went back to the 50s, you would even see a bigger growth. So we're going to type this data into our two lists in our calculator. T, or X for our calculator's purposes, but for our model, T is going to be the number of years since 1950. So if I put right up here T, what would be the value for T? Did I say 50? 1970, sorry. So what would be the first value for T based on 1975? 5, because 1975 is 5 years after 1970. 1980 would get a what? 10, 85, then 20, 25, and 30. So those are the numbers we're going to put into our list. So to remind you how to do the lists, we go into, first we turn on our calculators, clear everything out. I'm going to clear everything out of mine just to make nice and, okay. So we go to the stat button, S-T-A-T, and we hit stat. We hit number 1 for edit, and we're going to edit our list. So I'm going to go over here, and to edit that list, I put my cursor up there, and don't ever hit delete here, clear, enter, because you'll delete the whole, and then clear, enter. So if you want to clear out your data, that's all you do. Okay, so it's going to be 5, 10, 15, 20, 25, 30. 5, 10, 15, 20, 25, 30. Okay. And now we enter, and mine's L5. You might have L1 and L2. It doesn't matter. So now we enter the actual data for the number of working women, and this is represented, the units here in millions. So we have 4.851, 5.886, 7.322, 8.732, 9.587, and then the last one is 9.736. Oops, I messed up. Clear. 9.587, enter. That always helps to enter. 9.736, enter. Okay, so I've got my two lists in. Now, the next thing you want to do is take a look at your scatter plot after you enter your data. So you go up to your the stat plot, which is right above your y equals, and since it's yellow, you hit second y equals. I go down to my first stat plot, and I'm going to turn it on. Notice this little icon right here tells you that you're going to be looking for a scatter plot. My lists are all done, and I'm going to use that little mark. And don't forget, hit zoom 9 for all your stat plots. So then you hit zoom 9, and you should get your scatter plot. So you look at that, and before we started working with polynomials, you might say, hey, I can put a pretty nice straight line through that, right? You start to notice that it's growing, 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 but these last two data pieces, it's starting to level off a little bit. So now that you know about polynomial functions as well as linear functions, even though a linear function is polynomial, you know a little bit more about other types of polynomial functions. At first you might say, well, let me try a linear regression, and then let me find another regression, okay? Maybe this would be better explained by a parabola. Maybe a parabola would fit it better. So let's take a look at this. So first you try your linear regression. You just go to stat, you go to calc, and you go down to linear regression. You hit enter. And again, you want to put where your lists are. Mine happen to be L4, comma, L5, comma, and then I have to tell it where to put it as an equation in my y equals. So I go to vars, and I go to my y variables, hit function, God bless you, and I say y1. Now I hit enter, and there's my linear regression. Remember now, this is a polynomial, so we use a as our leading coefficient. B is like it always is in the y equals mx plus b model. That's your y-intercept. That's your constant term. Can you get that, Doralena, please? So the linear regression is y hat equals 0.2111. I'm going to take it out 4 places just to write it down. But when you do your calculations, you keep the whole equation in your calculator, times t, because that's the variable we're using here, plus 3.992. Now, because the correlation coefficient can only be used for straight line data, and we're now going to be needing another statistics that we can use to see which one of these regressions is better. We're going to use R square for any type of regression we do now. So you notice your R square is 0.959. That's pretty good for an R square. That means that 95%, almost 96% of the variation in this data can be explained by this regression on the year. So there's a little bit of variation. It's not perfect, and there's something else going on other than the year that explains that. Okay, so you might be pretty happy with that, and let's see what the graph looks like. And if you look at that line, it's pretty good. So let's take a picture of that. I'm going to put it right here for us. So this is the time in algebra where everything is not like there's a definite right answer all the time. And that's kind of like the life of being a statistician. You deal with best fit models, and you deal with a little bit of what we call probability. It's not like solving an equation and having the exact right answer. So here you say, hey, that's a pretty good fit. But I'm curious to see what a quadratic fit might look like. So you've already got your data in. It doesn't take you too much of an effort now, because all you have to do is go back into stat, hit calc, and say, I want to try a quadratic regression on that. I want to see how a parabola might fit that. So you go down to quad regression, hit same thing, second L4, comma, second L5, comma. You go to your vars button, y vars, and then you hit enter. And we don't want to put it in y1 because that's where our linear regression is. So I'm going to go down to y2, hit enter. And now let me see what that model looks like. Now you should be expecting 3 terms because it's quadratic. Your leading coefficient here is negative 0.004824. So the equation for our parabola is negative 0.004824 x squared My linear term, the number multiplying x, is right here, 0.379924x. And my constant term, c, is 2.8662. Notice my r squared value is 0.986. So that tells me now I can compare these two r squared values. Notice that the one for the linear regression is a little baby r because it's the square of the correlation coefficient. This r has a capital R. We can compare these two. And when you look at the graph, let's take a look at the graph. Oops, I forgot to do zoom 9. Okay, good. Zoom 9. So there's your straight line, and there's your parabola. And you can see, in fact, I'm going to turn off my straight line just so you can see how well the parabola fits this data. Zoom 9. Okay. Even though the line was a really nice fit, that's even closer to all those points. The little deviations, the vertical deviations, are much smaller. Okay, so let me take a picture of this and we'll plot this right down, plunk this right down beside it. Let's make these a little smaller so we can get them both in. So later on, if you need to watch the video, all the info will be there for you. Okay, so if you were going to use the linear and the parabolic model to predict the number of women with children below the age of 86 in 2011. Okay, so we're talking about 2011. So that's another 11 years from here. How confident are you in the accuracy of your prediction for each model? So in other words, if you were going out here another 10 years, another decade, this model continues to rise like this, and this one is still increasing a little bit. Okay, we know that at some point it's going to start to head back down, right? Because look at the leading coefficient right here. The leading coefficient on my parabola is negative. So that means my parabola at some point is going to start to turn around and start heading down towards negative infinity. Okay, but for 11 years from now, which of these models do you think you would feel most confident about? How confident would you be in the linear regression model? So, okay, pretty confident. And here you're saying really confident? Okay. Okay, really confident. Okay. Even though this is going to continue to go up, and maybe the number of women in the workforce isn't going up quite as rapidly, but it still may not be too far away from the actual point, wherever that might be. Okay. This one is starting, it's still increasing a little bit. And then we know it's going to start to go back down. We don't know exactly where it's going to start to turn back down, but as Tony said, he thinks maybe that one may be a better fit in terms of accuracy. What about trying to predict 2030, extrapolating, going way outside the data? Which of these models do you feel confident about? Huh? Linear. Okay. So the linear may be way up here, even though we see start to be leveling off. What about the quadratic? Is that going to be good at all? Yeah, we don't know when it's going to go back down, but we do know it's going to go back down. Let's say 2050. Would you feel good about the parabola? No. And what about this? Linear. We're getting kind of iffy here because we're going too far outside the data. If we had data for 2010, we might feel a little better about trying to look at either the straight line or the parabola. But if we're going to go out another 36 years, you're gonna be in serious, like, iffy territory if you go too far outside of your data, because polynomials will rise very quickly or drop very quickly. So anytime you go outside your data set with polynomial regression, you could be kind of skating on thin ice. So if we use the leading coefficient test to determine the end behavior to the right for each model, which model do you think? So with our straight line, our leading coefficient is positive. So that means our right arm is up. With our parabola, our right arm is down. So if you just use that idea, which one do you think would be more accurate for predicting the future, linear or the parabola? Just based on those two, if you had to make a choice. Parabola, so you think it's going to go way down to negative numbers of women in the workforce? Right, so this is saying, which model do you think would be for future number of women? You can't, but we're saying just looking at the end behavior, just the end behavior of each model. Do you think it's ever going to go down rapidly to negative numbers? No. But the question is, will it continue to grow? It's not growing at a huge rate. What does this tell you? The slope tells you that it's 0.2 million per year, right? 0.2, 2/10 of a million, right? So how many thousands is that? 200. So this is like about 200,000 women a year. So that's not a lot. But again, with the economy and everything, who knows, right? So it's a little bit of an iffy kind of situation, and you've got to be a little careful. But in terms of this data, to model this data, the quadratic regression would be the better one, okay? Okay, so here's your 4-step modeling process. You create a scatter plot of the data. You decide whether a line, a parabola, or some other curve. You might find a cubic is better. If you see like the data that we started off with the US energy consumption, if it has 2 turning points, you might try a cubic regression. You want to find something that comes close to the points. The more peaks and valleys the data has, the higher degree of the polynomial you'll need. Okay? Find an equation for your model. Verify that your equation has a graph that comes close to the points in the scatter plot by doing zoom 9 and looking at how close it is. Use your equation to model and draw conclusions to make estimates and predictions. Because the end behavior of a higher degree polynomial rapidly tends to either positive or negative infinity. Remember, the higher the degree, the quicker it goes towards infinity in either direction. So a straight line is not going to approach, even though it increases without bound, it's not going to go as quickly as a parabola would with a positive leading coefficient. So extrapolation is a subject to a higher risk of producing meaningless results. You have a bigger chance of model breakdown. Okay, if you go too far outside of your data set, that's what extrapolation means. You're going outside of the data that you're actually graphing. So at the beginning of the modeling process, we have to decide whether a linear, quadratic, cubic, quartic, or whatever is the best situation. So here's some criteria, because as I said, this is a fairly open-ended kind of situation. The graph of the model should fit the points well. So whatever graph you choose, it should fit it well. And that's where you look at your R-square value. Okay? Use the simplest model that captures the pattern of the data. In other words, if you say you have a linear model and you have let's say you have a cubic model and a model to the 5th degree. Okay, and the R-squares are relatively close. You always want to go with the simplest model. So go with your cubic, go with the lesser degree because it's easier to use. The model should make sense within the context of the real world situation. So the quadratic parabola regression, even though it had a better R-square, if we went too far into the future, it doesn't make sense that, well, again, unless we start to see between 2000 and now, there's been a drastic drop in the number of women in the workforce. We only know that if we go to the US Census Bureau and we look up the data. Okay? So today you have the entire period. For those of you that came in late, we are on lecture 27, which is the back part of 26. So you're going to start today. You have This is your homework. You have to do these problems, 4 problems, since you don't have homework on my math lab. All of the steps are here, so you can get going with this today. And let me know if you have any questions. I'll come around and check out your regressions. So today we're doing polynomial regression, and we've already done some polynomial regression when we did a linear regression, but we're going to be looking at linear regression, and now we're going to move to higher degree models like quadratics, cubics, and maybe even a quartic. What do you think quartic is? What degree? 4, right. Don't forget that your project 4 is not due to next Wednesday, but I need to see and put a little check mark on your student ID polynomial by Wednesday, because I don't want you doing the whole thing incorrectly. So please show me that by Wednesday. You have a quiz on Friday on classes 23, which is your quadratic function section, 3-1. And then 24, remember, was our test. And then 25 through 27 covers the 2 lectures on polynomial functions and today's class. So that's Friday's quiz, 23, 25 to 27. And whether or not you do homework or not for this class, I'd like everybody to do the preview exercise number 110 on page 364. So if you could write that down, exercise number 110 on page 364 prior to the next class, because in the next class we're going to be dividing polynomials, and this problem will just help you review division, longhand division, which is going to be important. I already got your progress reports out. That was for my first class. So you probably only get it if you're failing or getting a D, but otherwise it just says what I put on the back of your test, your grade that's there. Okay. All right, so this is what I want you to do for Wednesday, and this is the stuff on your quiz, so let's move along. So polynomial regression. As I mentioned earlier, we entered data into our calculators and performed a linear regression. Now, if you recall, with the linear regression, we calculated a correlation coefficient, which we assigned the little letter R. That stood for the correlation coefficient. And remember, the correlation coefficient roamed between +1 and -1, with positive and -1 being a perfect linear fit. So R told you how strong your linear relationship was. Given today that we're going to be looking at data that will not be straight lines, R is not going to have any value to us anymore. But if you recall, along with your little R value, you saw an R square value on your linear regression. Now, we didn't use R square when we were doing linear regression. This is called the coefficient of determination. It's got a really fancy name in statistics. And if you're really interested in knowing what this is, I can explain it to you, and I'm going around and helping you. It's more for a statistics lecture. So in order to compare the different models we're going to look at today, we're going to be looking at R square, okay? Because R, you can't calculate R for a quadratic, because there's no linear relationship in a quadratic. Now, if you're looking at a linear relationship, it's little baby r. If you're looking at anything higher than a linear relationship, you're going to see big capital R. This is other polynomial relationships, other polynomial regression. So let me change that word relationship here to regression. So today, if we're looking at different models and we're trying to figure out what's the best one to use, you look at your R square values, and that will help you to determine which model is the best. Okay, so we were looking at this model last Wednesday. This was the U.S. energy consumption measured in quadrillion BTUs. BTU stands for British Thermal Unit. It's just the units they use for energy consumption. And we were telling the story from 1960 to 2000. And we fit somewhere along the way. I had you try to fit a curve to this that you thought was the best fit. Okay, so you all drew different curves, and we ended up looking at, I don't know if we ever actually put this into our calculators, but we could. But if I asked you this next question, if I asked this in my first class, and it took us a little while to get there, but I was hoping based on what we talked about in our last class, we could get there a little quicker, but hey, it's learning. So if I asked you the following question, what is the smallest degree polynomial that fits the data the best? So what's the smallest degree polynomial you think we could have for that particular curve? Cooper? And why did you say 3? Okay, right. So we go back to that idea of turning points, right? We have a turning point here, which is a relative maximum. And we have a turning point here, which is a relative minimum. And we had that handy dandy little formula that said that depending on your degree, you could have at most n minus 1 turning points. So if n minus 1 equals 2, if we have 2 turning points, and you add 1 to both sides and you get n, which is your degree, has to be 3. That's the smallest it could be. It might be a 4th degree, it might be a higher degree, but that's the smallest it could be. Okay. So if we go back and we take this data, this was class 25. Do I have class 25? I think it was class 25 where, did I actually give you the real data for this? No, I didn't. I thought I did. You know what? I have it in I have a table with it in. Well, we could estimate, I think, based on this. So let's suppose I have the data and I want to do a regression. Well, we talked about why we wouldn't use a straight line in class and why we wouldn't use a parabola. So we think a cubic might be a good fit here. So I'm going to do this a couple of times. It's all written down in the last page of your lecture notes. I'm just going to go through this to review regression again. So you can just sit back and relax. You don't have to worry about copying anything right now. I'm just going to clear everything out from my first class, turn all my stat plots off so nothing is in the way. Okay, so first thing you do is you have to enter your data. You go to the edit button, and remember to clear out your list. Don't hit delete because then you'll lose it. That's why I'm starting at L4 instead of L1 because I hit delete. So to clear out the list, you hit clear, enter, right? And that clears out that list. And now I go over here, clear, enter. Okay. So remember I started with 1960. I called X the number of years since 1960. So I'm going to say 0, 10, 20, 30, 40. Okay, that takes me up to 2000. And now let's just estimate here. That looks like it might be like 13. No, maybe 12.2. You know, this is a real quick estimate here. At 1970, it looks like it's just under 22, right? So I'm going to say 21.9. And that looks like about 20.2. And that looks 19.5. Again, this is all just, and that's 24. All right. So no, first I have to get my scatter plot when I enter my data. So let's suppose we didn't have this picture. Your scatter plot, remember, is a graph. And so, but it's a statistical graph. So you got to come up here to your stat plots. You enter, you turn it on. Your first icon here is a scatter plot. You have to make sure here that the list where your data is right here. Mine's in L4 and L5. And I always use this little box. But before you hit graph, You want to tell it to zoom 9. That's your zoom stat. So you hit zoom 9, and there's your graph. And that's pretty close to ours, except for notice our first data point is at 0, right? Versus this little break in the graph here. All right. So now I want to fit what I think would be the best fit curve to that, which I think is a cubic. So I go to my stat button, I go over to calc, and I go down here to where it says cubic regression. And where is my data? My data is in L4, comma, L5, comma, and this is the part everyone forgets. Remember, I want to put the equation into my calculator so I can use it to make estimates and predictions. So I got to tell it where to put it, and that's in my Y variables. So you come here to the vars button. That's the one that we forget after we don't use it for 100 years. So we put vars, and we say, let's go over to my Y vars, and I'm going to put it in Y1. And now I hit enter. And there's all my data. There's my equation. It's a cubic, and this is my leading coefficient. My leading coefficient's small, but it's positive, right? Which tells me my right arm's up, good. My left arm's down, all right? So my predicting equation here is 0.001383 x cubed. That's my leading coefficient. So that fits with my graph with my right arm up and my left arm down. B is the coefficient for my x squared term, which we call our quadratic term. So let me make this a minus. And let's get that value in. Now, when you write it down in your paper, you're not going to write all of these places in. You're going to estimate it. But if I asked you to make a prediction, well, let me get this down first. And then C is 1.6702x, and then your constant coefficient is 3171. Okay, your R square value is the highlight here. Your R square value is 0.987, or we can call it 0.988. The highest you can be is 1. There's no negatives here because we're squaring. That's a really good fit. So let's copy this down so we can put that in our notes. So you can see how to get the equation from all that information. Notice I use this little hat over my Y. Your book doesn't use that. Well, your book doesn't show you this. That's why you won't have any My Math Lab homework for this. It's supplement. So the only homework you have are the 4 problems that you have at the back of this packet. You'll have most of the class today to work on that. So there's all the information to get the polynomial, the cubic regression. Now let's take a look at our picture. So I hit zoom 9, and there's my curve, and it fits it really, really tight, doesn't it? So this would be an excellent model. Woohoo! What happened? Ooh, where's my? Okay. So this would be an excellent model for trying to predict or estimate the U.S. energy usage, particularly between 1960 and 2000. Like if I wanted to ask for 65 or 1995, where could I possibly get into trouble? Yeah, before 1960 or after, because polynomials, especially the higher your degree, it rises or falls really very rapidly. So this is increasing really quickly. The question is U.S. energy consumption increasing that quickly? So anytime you go outside your data set, you could run into problems quickly with these higher degree polynomials. Okay, so this is your scatter plot with your cubic equation plotted. Now let's suppose I asked you to predict the U.S. energy consumption. Now this went through 2000, right? The U.S. energy consumption in 2010. Okay, So first of all, what would my x value be? 50, because we used 1960 as our initial base year for 0. So x is going to be 50. So this is where a lot of my students were having trouble. They're like, so some students, like, they really cut and estimated these numbers to write them down because, you know, there's a little bit of laziness that goes on. So they would use this equation, their equation with not all of the accuracy that you get in your calculator, and they would put 50 in for x. So their estimates, they were compounding the estimate error by doing that. Whereas you've got this entire equation right there in your calculator with all of the incredible precision of having decimals out that many places. So how could you put 50 in and get your answer? What could you do? So you can have your calculator do all the work for x equals 50. Use your table, right? So set your table first. You can set your table to say I'm going to start at 0. You can start anywhere where you want. You could say I'm starting at 40 or 50. It doesn't matter. And here's the key right here. Go down and hit the independent variable, which is x. Hit ask. So now when you hit your table, it's asking you, what do you want me to make a prediction for? I want a prediction for when it's 2010 or when x is 50. So I throw a 50 right in there. Boom. There's my estimate, 44.46 quadrillion BTUs, right? So that's how you can use your table to do some of this calculation and not compound your error, your estimation error, by using as much of the data as much of the precision and accuracy of your calculator. So this says that in 2010, the US energy consumption will be 44.46 quadrillion BTUs. Okay. So that's a quick review of how you put all your data in, how you do your regression, how you get your equation, how you make predictions. Okay. So I didn't intend to do that when I put this little picture in. What I intended to do was this particular situation. So let's take a look at this. I've done some of the work for you already. I've got some pictures here. This table shows the number of full-time women in the civilian labor force. So this means women who are in the military. I'm trying to remember if civilian force by census is just military, if they include like police force. I don't remember. I know if you're in the military, you're not included in this. With children under the age of 6 for selected years. So first you look at this data. What would be, if I didn't have the pictures there for you, what might be your first comment on the trend that's happening here? What would be your first comment? It's increasing. Over time, the number of women in the labor force has been increasing from 1975 to 2000. Okay. So the first thing you're going to do is what we did a minute ago. Let's put all this data right into our calculators. So if you have your calculator, you want to pull it out now. If you don't have a calculator, I have a few up here if you need one. Does anybody need one? No? Okay, good. Okay, so let's enter this data. Please put your name up on the board. Okay, so let's see how we're defining our independent variable. Number of years since when? Number of years since 1970. Okay, so T is going to equal, let's put the T right above each one of those. So the first value, T is going to equal what? Number of years since 1970, and the first data point is 1975. So what do I put in for T? 5, 10, 15, 20, 25, 30. Okay, so I go to my calculator, and in my first list, I do 5, and then I just increment by 5, 10, 15, 20, 25, 30. Okay. Now, in my L5, I actually put in the number of millions of women that are in the force, 4.851. Enter, 5.886. Enter, 7.322. Enter, 8.732. Enter, 9.587. Enter, and then the last one is 9.736. I just want to take a minute because I don't know which class it was, but remember when you did project 2 with the linear regression? Someone in one of my classes had data that I wrote. We could probably model this with a polynomial function. Does anybody recall if their data maybe had some peaks and valleys in it at all? Might have been my first class. All right. Okay. You can look later. But I'd like to get that data back, and I could use it on a quiz or a test. Anyway, not ours. You can't have it? I can't have it then? Okay. All right. So there's the data. And again, we don't know what kind of equation we're going to use yet, what kind of regression, until we look at the picture. So you always got to get your stat plot. And let's clear out. Now I'm gonna keep, as you go through this work today, keep your data in each equation, but I don't want this particular model turned on anymore. It's going to affect my, I'm going to have all kinds of curves and lines going through my scatter plot. So I just turn that data off, that equation off, and I want to get a scatter plot. And I'm going to use exactly the same L4 and L5. So let's take a look, zoom 9 first. So there's my data points right there. Now, previous to today, you would say, hey, I feel pretty good about a straight line going through there, right? And if you do a linear regression, this is what it looks like right here. There's your linear regression. So let's see, again, let's review how we would get all the info for our linear regression. Calc, go down to linear regression. You put in L4 or L1, whatever you're using. Now, I already have something in my Y1 variable, and I want to keep it there because in case Linda comes over and checks my paper and asks me how I got my equation, I can go back and show her. So I'm going to put it in Y2, my other slot, hit enter, and there's my linear equation. My R square value is 0.95, 0.59. And what's my equation look like? Y hat equals, what's my slope? What's my slope? 0.2110742.857. It's your leading coefficient. It's called A now in polynomial, A sub 1, but your leading coefficient here is your slope. Instead of seeing an M there, it's A. So it's 0.211, we'll just call it 1x, and then we have 3.992. Okay, so that's the linear regression. Y vars, well, you'll see for the next one, okay? All right, so now someone said in my other class, yeah, but I think if I started a quadratic, I could see this maybe a quadratic fitting this, just part of a quadratic. So here we go, let's try a quadratic. Stat, calc, I'm going to go down and try a quadratic regression and see how I do. So I put my two lists in again with my little comma between them. And now I tell it, I want you to go into my Y variables list. I've used Y1 and Y2. So I go to this vars button right here, hit vars. I scoot over to my Y variables because that's where I want to go. And I've already taken up Y1 and Y2. So now let me do Y3. And if you want to see both your line and your parabola in the same picture, then don't turn off Y2. If you just want to see your parabola, come down here and turn off Y2. You don't want to see a line. So now we want to do zoom 9. Okay, and why don't we see anything? This happened a lot in my first class. Did I actually put the equation in my y vars yet? Did I do it? No, I didn't do it. So you're not gonna get your picture until you tell it where to put it. Okay? So let's clear this out. Let's go back here. You got to tell it where to put the equation, or else you'll never get the picture of the equation. L4, comma, L5. Now I'm going to put it in my y variables, scoot over, and I'm putting it in Y3. Now to get the picture, well, if you want your equation, there it is. All right. It says, what's my leading coefficient here? The first letter of the alphabet, A. It's negative, which tells me my right arm's going to be down and my left arm's going to be down because this is an even function. Okay. Now, I don't see the whole function, but that's what I know about its end behavior. R squared, notice big capital R now is 0.986, so it's a better fit. So when I look at the plot, zoom 9, you see that the curve here is much closer. Well, it was close with the line, but that fits that data pretty well. So again, I remove the equation. Doesn't matter right now for our purposes. So use the linear and the parabolic model to predict the number of women who are working with children in 2011. So let's do that. How are we going to do, what do we enter now for X? Let's go back. X or T. Oops, I did a typical thing here. What's my variable here? T. So what should I have in this model here? T, right. So this should be T. All right. So notice I didn't get rid of any of my lines. So if I go back here, T is since what? 19 what? I forgot already. 70. So 2011, what will be the value of T for 2011? What year is 0? 1970. So 2011 is 41 years from, I don't know. It says right here 1970. Okay. Yeah. So let's go and see what our linear model predicts for the number of women in the workforce 41 years from now. Okay, so let's go out here. Here I'm going to use my tables. So look, where are my two equations? Here's Y2 is my linear regression, my line of best fit, and Y3 is my quadratic regression. So I'm going to go to my table and I'm going to ask it to predict for 41. And there's my prediction for my linear regression. It's saying it's 12.646 million women. And my quadratic, notice, is at 10.33. So the number of women, ooh, that got small really fast, didn't it? Ooh, there we go. So we can see it. So the prediction for using the linear model was about 12.6 million women in the workforce. And with my parabolic model, it was 10.3. And if you think about this, look at the picture a little bit. Notice your straight line is going, it's increasing. I'm going out here to 2011, whereas this is kind of curving. This is probably going to reach some kind of maximum soon, right? It's still increasing a little bit and then it's going to drop, right? So if you were using one of these models, given the data set right here, which one would you feel more confident in, the parabolic model or the linear model? Parabolic. This one isn't too bad. My confidence level here would be pretty good. But right now, given that 2011 isn't too far outside my data set, I'm extrapolating outside of my data set, but it's not too far out. I'm feeling really good with this parabolic model. If we go back to the leading coefficient tests and we think of just the end behavior of our two models, which model would be the most accurate in predicting future women in the civilian workforce? If we look at our end behavior, and we're going way out in the future, which one do you think would be really totally awful, even if the other one may not be as accurate? What do you think? It's women with children under the age of 6. Right. So which of these models, if we just think about the end behavior, what's going to happen to the end behavior with this quadratic model? It's going to start going down, and it will start predicting negative number of women, right? So that's not going to be very good if we're just thinking about the end behavior. The linear model is going to continue to grow. Now, whether women continue to grow at this rate, which is what your slope here tells you, you're increasing by 0.2 million each year, or 2 million every 10 years. All right? So whether we continue to grow at that rate or not is debatable. All right? But I know I'm not ever going to be negative. So the parabolic model is good right now and maybe shortly into the future, but at some point we're going to have model breakdown. So the moral of the story is sometimes you can look at a couple of different models, and when you're trying to decide which model is the best, first of all, you want to look at your scatter plot. You want to make sure your model is a pretty good fit to your data points. And whenever you have a choice, when both models are strong, you always go for the simplest model. So if you had a degree 5 model and a degree, say, 2 model, and they were both pretty close, their R-squares were pretty close, then you would pick the quadratic. Okay? So the moral of the story is be as simple as possible. Make sure your model makes sense for the real world situation. If it shows that it's going to go to negative pretty quickly, then that's not going to be very good. You're going to have model breakdown. So you have 4 data sets to explore today. Notice this first one asks you to find the vertex. I just want to point out to you that a vertex on a quadratic is either its maximum value or its minimum. So all you have to do is go to second calc, and go down to either maximum or minimum depending on your story, and hit enter 3 times, and you'll get your maximum value for that model. Okay? Or you could do it by hand using negative b over 2a, that little formula we use for quadratics, to help you review. Okay, so you have 35 minutes to work through these data sets. You have your flags, you have each other. Ask me if you need help, and I'm here for you if you need help.